Right. All right, guys, let's settle down. So thank you all. I'm Ryan. I'm your host for the Applied Economics Student Seminar in the Skill Series. Just to set some ground rules, this is going to be an hour presentation at 3 o'clock on the dot. We're going to have another class come in here, so we're going to have to rush really quickly out. So about 10 minutes to the hour, just think about, I got to get out of the room. But today I'm really excited to have Terry here. And he's going to be presenting Writing Theory for Reduced Form Models. Terry is the interim division head for the Applied Economics Department and the Austin A. Dowell professor. Terry's research focuses mostly on probability, risk, and regulatory emergence of agricultural technologies. Terry has written several empirical articles and theoretical papers that have featured in Nature, the Journal of Public Economics, Science, the American Journal of Agricultural Economics, and Food Policy, amongst others. He has taught for several years the PhD level microeconomics sequence, and Terry is a champion of both reduced form models being in applied economics PhDs, dissertations, as well as in published work. So let's welcome Terry.
Thanks, Ryan. Thanks for inviting me to talk to you guys. Ryan essentially came up to me and said, "Yeah, would you be willing to talk on reduced and structural models and their differences?" And I said, "Well, okay, I guess." I've used both, so I'm certainly happy to talk about it and give you my thoughts and just give you some, what is the relationship, how do they differ, and how can they be used to one way or the other. So the purpose of this talk then is theoretically illustrate the distinctions between structural and reduced form models. We're going to use cost minimization, profit maximization kind of as a place to start and to think about these. We'll do a specific example so we can actually put some more concrete stuff. We focus on a Cobb-Douglas, which is easy. Number one, it solves like really nice, but we'll also see that it has. But we'll also see that it has some potential problems. That's working out? Yep. Okay, and then we'll discuss the challenges in terms of parameter interpretation, hypothesis testing, when answering common econometric questions. Okay? I want this to be more of a conversation than a lecture. So I'm going to be asking lots of questions and offering. Can you hear okay? Okay. Okay, so let's make this concrete. So we're going to think about a common economic question. I do a lot of ag econ stuff. So the question we're going to think about here is we're interested in the relationship between fertilizer and seeding rates. So you may think of yourself as working for Corteva, which is a big seed and chemical company, and trying to figure out, well, fertilizer prices have been going up, and so does that mean I need to be producing more seed because farmers are going to want more seed for corn, to plant corn, or are they going to want less seed? Of course, if we want to frame this as a question, we could ask, does increasing fertilizer price increase corn farmers' seeding rates? All right, and so so how can we answer this question? All right, so the place we'll start is we're going to go up the hill. How many people have been up the hill? So like Borlaug Hall, soil science, okay? And soil, water, and climate. We can ask ourselves, okay, how did they answer this question up the hill? And the way they'd answer this question up the hill is they'd want to say, okay, well, what's the relationship between, corn yields, bushels of corn, and how much seed you plant in a given area and how much fertilizer you put down, all right? So to answer this question, they'd say, okay, well, let's find a field, and we can partition that field into small research plots, and then we can assign treatments to those different plots in terms of different combinations of fertilizer and seeding rates, okay? And we want to do that. We want to do replications. So for some of those combinations, we want to do them more than once. Okay, so we'll do it more than once. And if you really want to be controlled about your environment, so you don't have a lot of potential confounders, we could actually go in a greenhouse, and we could do this in a greenhouse too with little small plots. Okay, so we then go ahead and, based on this design that we've done and this randomization across this field, we can actually do that, fertilize, plant the seed, let the corn grow, harvest the corn, and say, okay, how many bushels how many bushels did we generate for each of these plots, all right? To then figure out, how much we did and how they differed between the treatments. There's a couple different regressions we could run. Actually, the guys up on the hill will probably do an analysis of variance, but another simple way we could do it is just do this simple regression here. In equation 1, Q TR is essentially bushels of corn produced for treatment T and replication R. So what are the parameters? The first parameter is just an intercept. All right. The next 2 to T, where T is the total number of treatments we decided to run, distinct combinations of fertilizer and seeding rates. We have dummy variables for each treatment, other than the first treatment, which we'll call the control treatment. All right. And then we got some sort of error here. All right. So we can run this regression. All right. Another regression we could run is this one here. And with this one here, we have ZF. That's going to be actually our fertilizer rate. And ZS is going to be our seeding rate. And so here we essentially have a quadratic form in fertilizer and seeding rates. All right. So then we're estimating that with respect to Q, the total bushels per acre. All right. So that's another regression we could run. It's telling us something about the relationship between how much we're producing and the various inputs. The third relationship here is, let's do a log model. So here we're taking the log of the output, corn bushels, and we're taking the log of how much fertilizer we use, and we're taking the log of how much seeding, the seeding rate that we used. Okay, we could estimate that, right? All three of these are going to tell us something. They're going to tell us something about the relationship between how much corn we're producing, how much fertilizer we're using, and what rating, how we're rating, how much seed we're putting down in a particular area. Okay, so what is equation 1 telling us? So when we look at equation 1, when we estimate these parameters, what are these parameters telling us? So if we go back to this equation and say we pick phi2, what is phi2 parameter telling us about or bushels of corn? Can anybody tell me?
Means.
Yeah, it's going to give us the difference in means. Difference in means between the control treatment, our treatment 1, and whatever our treatment 2 was, right? So maybe treatment 2 was a seeding rate of 35,000 seeds per acre and 120 pounds of nitrogen per acre, all right? So these parameters are going to tell us essentially the difference between each of our treatments, all right? And we could then, also compare them to get differences between other treatments. But so that's what that's telling us. Well, what about equation 2? What is equation 2 telling us? Well, one way to think of equation 2 is it's actually a Taylor series approximation, a second order Taylor series approximation of some general yield function or some general production function that, it has to be differentiable, right? If we're doing Taylor series expansion, we assume that this function is differentiable. It's got 2 variables, seeding rates and fertilizer, producing corn. But essentially that's what we can look at that as an approximation to some general production function, a differentiable production function. If we look at the parameters in this model, a parameter that might be of particular interest to us is what is the interaction between seeding and fertilizer rates, right? And this BF, where'd it go? Over here. This BFS is really giving us the interaction, all right? If it's a positive interaction, that tells us that, if we increase our fertilizer, we're increasing the marginal productivity of seeding or seeding rate. Alternatively, if it's a negative, it's telling us the opposite. If we increase fertilizer, that decreases the marginal product of increasing our seeding rate. All right. So that's what that gives us as our. And then we've got this third equation. This third equation, really what that represents is a Cobb-Douglas. Assumes that we have a Cobb-Douglas production function in seeding rates and fertilizer use. And if we look at the 2 parameters, TF, tau F, and tau I, really what we're interested in is the product of those 2. And if the product of those 2 is positive, then again, we have this synergy between fertilizing and seeding rates. If it's negative, we have, kind of a, one decreases the marginal product of the other. Okay. All right. So any questions on that? Does everybody understand what these regression equations are doing, what they're going to give us? All right. So let's ask this first question. So what it, okay, so we estimate this production function. How do we know how is a farmer going to respond to a change in fertilizer price? How can we use these results to figure out how a farmer is going to change their seeding rate in response to their fertilizer rate?
Marginal rate of technical substitution.
Marginal rate of technical substitution. Okay, so what I'm going to look at, so you're going to look at how the slope of the cost curve, right,
Yeah.
affects the marginal rate of substitution or changes in relation to the marginal rate of substitution. Yeah, so we can do that. So essentially, but what does that mean? So that's what is that problem you just solved? It's a structural problem, but it's also behavioral, right? Cost minimization problem. So you're thinking of the cost minimization problem, and if we say, okay, well, let's use this production function, let's solve the cost minimization problem, and then we can use that to figure out, okay, does a farmer, if we increase the price of fertilizer, are they going to use more or less seed? Okay. So if we add some assumptions on how we think a farmer is going to use this production function, we can then make predictions about what, to answer our question. All right, so that's right. So that's easy enough to do with equation 2, right? Because equation 2 is essentially giving us a function, a differentiable function. That's okay with equation 3. Again, we have a differentiable function, production function. But what about equation 1? Equation 1 now, that's not a nice smooth functional form that we can deal with, right? That is actually just different means. Essentially, we've estimated the mean for each of the different combinations, right? So in that case, it's not exactly easy to see how you might answer the question. I mean, you could say, okay, well, let's look at all the treatments where we used 120 pounds of nitrogen, and then look at the different seeding rates at 120 pounds of nitrogen and see if it's increasing or decreasing, that relationship. Those means are increasing or decreasing, right? Or we could change that and say, okay, well, what about 90 pounds of nitrogen? Or is it increasing or decreasing? So we could use that to kind of get some of the same kind of information here. But with equation 1, it's a lot more flexible. So we could see a U, we could see a squiggly, depending on how many treatments we have, right? So it's actually really flexible. There's no functional assumptions here. This is as flexible as we can model this relationship. Whereas these are opposing functional forms, right? These make it really easy to kind of see maybe how a farmer would respond if we assume cost minimization. This one is a little bit harder, potentially a lot harder. And you're limited to the treatments that you explored, right? As opposed to generalizing or extrapolating beyond those treatments. Second question here. Which of these 3 models would you say are structural, and which would you say is a reduced form? Any thoughts? And what would your justification be? Go ahead, Thomas.
I would say that 3 is the structural approach because you have an implicit production technology that's included there, whereas in the Taylor series approximation is a reduced form because it's kind of a simplification of like a local version of it.
So 3 is structural. What about 2? Did you say 2 is structural too, or no?
I think 2 is reduced.
You just consider 2 is reduced, and then 1 is
super reduced.
Super reduced. So there are kind of different definitions or different thoughts of what a structural model is and what a reduced form model is. Back in the days when I was going through econometrics and stuff, a reduced form model was a model where essentially you've solved out any endogenous variables, and what you're left with at the end of the day is a function that depends only on exogenous variables. Now, by that definition, what are these? They're all reduced form models, right? They all depend on exogenous variables. Okay. So more recent definitions of reduced form models is that we're trying to get rid of functional form assumptions. All right, we're trying to get rid of the functional form assumptions as much as possible. In which case, this is the most explicit about what the functional form has to be. This is just assuming there's some differentiable relationship. And this one is as flexible as you can get. It doesn't assume any functional forms, right? So in this case, Thomas is right. So this one is the most structural. Then this is, you know, reduced structural a little bit, and this is absolutely reduced by definition, by the definition. Okay. All right. So any questions about that? So let's walk back down to Rattan Hall and say goodbye to our soil scientist friends and say, okay, well, how would an economist attack this problem? Right? Oh, we already talked about that. So how would an economist attack this problem? So first we would ask ourselves, okay, what behavioral model do we think applies here? What do we think it is that how a farmer is making a decision, right? Our two good, you know, two models that we like to use a lot are cost minimization or profit maximization models. The second question is, what is the hypothesis that we really want to test here? What is, you know, this relationship that we really want to test? Third, you know, how do we, you know, what data do we need to collect to actually test this hypothesis, given what we've specified in parts 1 and 2? Then we need to collect the data, and then we're ready to run some regressions, right? Okay, so let's think about that process. We talk about our potential behavioral models, cost minimization model. We say, okay, we're going to multiply our price of inputs times our inputs, and we want to make that as small as possible while we're able to produce the output Q that we want to produce. All right, that's the cost minimization problem. The solution to our cost minimization problem is essentially our optimal outputs that depend on the output, excuse me, our optimal inputs that depend on the output that we're trying to produce and the prices that we face. And then we'll say this E thing here, which is E is kind of idiosyncratic variation in the production function up here. All right. Profit maximization problem. Well, we're going to use duality here. Instead of going all the way back to the primal cost, we're going to just use our cost function that we just derived. We're going to subtract that from our revenue, and we're going to solve this problem, all right, by picking Q. What does the solution to this problem look like? Well, it's going to give us what we refer to as our supply of corn. All right, that supply of corn depends on the price of corn. It depends on our input prices, our input costs, and then this idiosyncratic factor that we'll put a little bit more detail to in just a second. All right, so these are kind of two different behavioral models that we could apply here. This one is essentially assuming competitive or exogenous output prices and exogenous input prices. What's nice about the cost minimization problem is we don't have to make any assumptions about the demand side, but we are making an assumption that the input prices are exogenously determined, that the farmer have no effect on those prices. All right. Okay, so that's our behavioral model. What are our hypotheses going to be? Or what should our hypotheses be? Well, this I'm going to ask you to remember your intermediate micro theory, where we talk about complements, goods being complements or substitutes, right? And so complementary goods, what do we know about complementary goods? If the price, if seeding rate is a complement to fertilizer, what do we think is the relationship between the price of fertilizer and the amount of seed or the rate that we seed at? Right? What's that?
Positive.
If they're complements, they're actually, it's going to be negative.
Oh, yeah.
Right? Because it's the price versus the quantity, right? The quantity should be moving in the same direction, but the price and the quantity should be moving in opposite direction. All right. Alternatively, if we talk about substitutes, then we see the positive relationship. Quantities go in opposite directions, but price and quantities go in the same direction for substitutes. All right, so we have these perfectly fine definitions of complements and substitutes that relate input or demands for things, which can be inputs, to prices of other inputs. All right. prices of other products. Okay, so we can also define these in terms of elasticities. But with these elasticities, you know, we can either look at things in terms of elasticities, or we can just look at them in terms of marginal effects, since these R, J, and T, those input prices and those inputs are positive, right? So they really just can divide out. So whichever is easier. We can use the elasticity formula, or we can use just the marginal products of, or excuse me, the marginal cross price effects to determine, to formulate our hypotheses. All right. So we have two hypotheses formulated here. One is if we use the cost function, if we assume cost minimization is what we're concerned with. The other hypothesis is framed in terms of the profit function. All right. Okay, so now we have our hypotheses well defined. How do we test them? How are we actually going to test these? Well, if we're going to be structural, well, let's make some more assumptions about what the structure of our production process looks like. And let's assume it's Cobb-Douglas. All right, so essentially what we have here is the production possibility set. It says we're Cobb-Douglas. Q has to be less than this exponential form of the inputs. All right, and here we have this epsilon, which is our idiosyncratic shock that could be different across different farmers. All right. Well, if we do our cost minimization problem, take our derivatives, do the bunch of algebra, we can ultimately write the log of our demand for an input as this beautiful linear equation. It's a linear equation of the log of our input prices and the log of our output. All right. It's a beautiful linear equation that, you know, you just like throw in, use OLFs, it'd be great. These parameters, you can say, okay, well, alpha, where'd alpha come from? Well, where'd alpha come from? These alphas all actually are just functions of our Cobb-Douglas parameters, right? So all these alphas are just, you know, they're non-linear. They're not necessarily nice little functions, but they're just functions of our parameters. All right. Okay, so you can think about it, this would be pretty straightforward to estimate, right? If you had right kind of data. When we look at this equation and we ask ourselves, okay, does this depend on exogenous things or endogenous things? What is the answer to that? Yeah.
Prices are exogenous, but Q is endogenous.
Yeah. All right. So we said prices, the R is the input prices, those are exogenous, but Q is actually ultimately the farmer has to pick how much corn they're going to produce. All right. So Q would typically be thought of as endogenous. So, okay, our estimation problem just got a little bit harder, right? We can't just do OLS and trust that we'll get unbiased parameter estimates. All right, so well, what can we do? Well, we can do the profit maximization problem to figure out what the optimal Q looks like, right? If we do that exercise with the Cobb-Douglas production function, then we get this log of output is this beautiful linear function of these betas parameters, all right? And these beta parameters, if we back, you know, again, like the alpha parameters, they ultimately just depend on our parameters from our Cobb-Douglas. They're complicated functions of these Cobb-Douglas parameters, but you know, they just depend on those Cobb-Douglas parameters, right? What's more to say here? Okay, so we go back to the question again: what's exogenous and what's endogenous in this equation? So here we have potentially the price of output and the price of the inputs, right? We said all this stuff is exogenous. So this is a nice little equation where we shouldn't have any endogeneity issues, right? Assuming our P's and R's aren't what else could create a problem here?
Monopolies.
Monopolies, yeah, but Yeah, there could be correlation because of measurement error or something like that. Could be creating correlation between these P's, R's, and these error terms. So it's maybe I may be being a little overly optimistic on how easy this is going to be to estimate. But anyways, we have this Q, and also with this Q now we can start to think, well, we have this Q equation, and we have this Z equation where we have an endogenous variable. You know, this starts telling us maybe how we can attack this estimation problem using instrumental variable methods, right? So we could potentially get to what we need here using an instrumental variable approach where we have our first stage equation for output defined by this equation, all right? Okay, but we also know from duality that we can take this Q equation and we can substitute it into this equation, and then we'll get an equation for our inputs that depend only on prices. So we can get rid of Q, right? Again, this is kind of nice because Q is endogenous and P is not endogenous, so we can get rid of that endogeneity by doing the substitution and then estimating this third or this ninth equation 9 now, estimating this equation essentially directly. All right, and we see what the parameter interpretations are here. Go ahead.
That's basically like in the back end, you're solving the optimization problem.
Yeah, so we could have solved the more primitive optimization problem. Here we're using duality, right? So we're using Shepard's lemma with a cost function to get the conditional input demand. Then we're substituting in the unconditional supply into the conditional input demand to get an unconditional input demand. All right, for those of you who haven't taken my PhD class, I drill this into your forehead, right? So if you forgot it, you should go back and review it, right? Okay, so this idea we could run this again. This is all exogenous, so presumably this would be an easy regression, although we're kind of ignoring measurement here, stuff that could also create problems that you want to deal with. All right. So any questions on kind of this layout? And this is all right, very structural. We've got a specific cost or a specific production function that we're using to build all this. Go ahead.
Does it matter with input photo or?
Yeah, we are going to have to be careful on how we're measuring. If we're doing it, if we've scaled everything to per acre, or if we're just kind of doing it, you know, in total. Yeah, so here I'm kind of more assuming we're kind of doing this all in total. But I mean, that's mostly just, I mean, that's not going to create any big difficulties in terms of doing the estimations. You just have to be careful that you know, that if you're doing it in bushels per acre, you need to make sure that your seeding rate is defined in terms of bushels per acre and your fertilizer rates are defined in terms of bushels per acre, just so that you're being consistent with how you're measuring inputs and outputs. Okay? Yeah, no, that's a good point. That's a good point. See, when I moved to this example, I have this big long Z, right? Before, when I did the kind of soil scientist, we just had two nice variables we had to worry about. When I moved to this, I said, oh, well, we got lots of Z's here, right? Well, that's right. If we do total, then one of these Z's would be how much land are we planting, right? Because that's going to be important to determine what the total corn production is. So that's absolutely right. And we haven't really talked very much about these other Z's. We have talked about these R's, right? And so the question is, do we have all the right R's in there? So another issue we could have is omitted variable bias. If we don't have all the right R's for all the inputs, all the relevant inputs in here, we could run into a problem of omitted variable bias, right? And that all relates, okay, well, what's in, you know, what is in that structural equation? And do we got everything specified in that structural equation, in that structural production function that should be in there? If we're missing something, we don't have that price, we could have be introducing omitted variable bias here. All right, and that's, you know, one of the weaknesses of structural models and structural modeling is, you know, how do you know you've got everything you should be in that model, all right? And that also gets a lot to what this error term is, you know, what is this error term? And if we don't have things, the right things in the inputs, in this error term, then we start to have to worry more about correlation between errors and other things.
So in reduced models, when you're thinking about covariate selection of controls,
Yep.
how does that relate in the sense of like, for a structural model, you have to make sure you have the right functional form across the whole
Yep.
equation. But when I'm thinking about just throwing in covariates, I'm thinking of it very linearly, like I'm just gonna throw you up on the right hand side.
Yep. So we'll come to that
Okay.
in a minute. Come to that in a minute. Yes.
So the goal for this process is to make sure that get the functions. First goal is to plot elements. Try to, by the algebras, just come up with the equations that are, basically constructed by the exogenous variables.
Yeah, that's right. So this equation is specific to the Cobb-Douglas form. If we chose a different production functional form, this might not be nearly as linear or nearly as pretty or easy to solve. You know, it could be that we can't really solve it, for a specific functional form. In which case, okay, how do we do the analysis? Well, we can't use OLS, or we have to go to other techniques to do the analysis if we can't actually solve it in a, it's easy enough. You could think of easy cases where you get some nonlinear equation. So then you have to, again, you can't use OLS. You have to figure out how to do, you have to do some sort of nonlinear methods. But you could even get it where you can't solve it at all. And then you have to do, again, different methods where maybe you analyze the first order conditions as opposed to the quantities, right? All right, so, okay, so we got these different equations that we could estimate. And when we add this structure, we need to figure out how that changes our hypotheses, or how can we test our hypotheses given this added structure? Well, for hypothesis C, it turns out that the elasticity that we're interested in, the cross-practice elasticity that we're interested in, is just going to be equal to alpha F, which is ultimately just equal to tau F over the sum of all the taus. Right? And so our question is that positive or is less than or equal to 0? Will tell us whether we have substitute relationship or complementary relationship. All right. Alternatively, for hypothesis 2 here, the relative parameter is going to be this delta ZF. That's going to give us our cross-price elasticity. And if we expand that out, you get this term, but that term actually simplifies pretty easily to this little guy here, which is essentially, minus TF over the 1 minus some of those TFs. All right. So what could we say here? Does anybody have alarm bells going off? Ding, ding. So we assume cost minimization. So cost minimization, you want to check or profit maximization. You might want to check your second order conditions, right? If you check your second order conditions, to have a perfect competition, you can't have increasing returns to scale, right? You have to have a marginal cost curve that swings up. In order to have a marginal cost curve that swings up, well, first of all, we have to have these tau Fs. They have to be positive, right? If you don't have them positive, then it's actually saying you have your as you increase your fertilizer, it decreases the amount of corn you produce, and that's that's not an assumption economists like. Right? Economists don't like an assumption where you put more input in and you get less output. We don't think people use those inputs, so we don't think we should pay much attention looking at it. All right. So that's one problem. But if that's true, if this TF has to be positive in order for us to have a well-defined problem, that means the sum of TFs has to be what? Also has to be positive. But that means, this whole thing is positive.
That's why you're using a 1 scale.
So we just, so this is essentially selling us, well, by theory, by the production function we assumed, we should get this result right here, right? We should be, right, a substitute relationship. So essentially the structural form we assume is, answer our question for us without doing any kind of data analysis. All right. So how do you fix that? Well, one thing is I could choose a functional form that's more flexible, that would allow for more complementaries and substitutabilities. One of the bad things about the Cobb-Douglas form is it does impose this substitutability across inputs. All right. I didn't do something more complicated because this math is already complicated. If you want to do complicated math, that's all you're doing in algebra. Right, but it's the same thing here. You'll be able to sign this, right, without, you don't need to do any more empirical analysis. But that assumes that our assumptions are all right. And we could have wrong assumptions. I'll throw out one more question. So what is the difference between these two hypotheses? Right, so one, we're testing this hypothesis through the cost function. The other one, we're testing it through the profit function. And what does this tell us? This is positive. This whole thing is positive. This is negative. But we have minus, one minus a positive number. So that could be positive or negative. But wait, if we think about returns to scale, we actually realize that this has to be less than 1. So this actually denominator needs to be positive. So this actually has to be negative. All right, so this cost function is saying, well, this is the relationship. It's a positive relationship. Profit function is saying, well, wait a second, this is the relationship. One's saying complement, the other one's saying substitutes. How can you have complements and what's going on here? How can we have this type of result where they're giving us exactly the opposite answer, but it's the same production function? What is the difference between these two hypotheses? Go ahead.
Is it that the second version, since it's the profit maximization function, it takes the revenue as not necessarily fixed, and so there can be a difference in allocated strategy, whereas the first one assumes that your output is fixed?
Exactly. So this one takes into account that if fertilizer prices change, that's going to change your marginal cost, which means you're going to want to change how much output you produce. The cost perspective just says holding your output fixed. What is your optimal trade-off? Right, holding your output fixed, the optimal trade, there are substitutes. If you don't hold the output fixed and you let the output vary according to competitive exogenous output prices, the Cobb-Douglas form actually gives you a complementary relationship for the profit function. The effect of the output side is bigger than the effect of the cost side. All right. But again, the bigger disturbing thing here is, well, I've already, just by choosing a functional form, I've answered my question. So why do I spend any money collecting data? Well, that functional form could be wrong. But that's something to pay attention to. If you're doing structural modeling and you're asking a question, make sure that you don't choose a model that answers the result without doing the empirical analysis.
So when you see a seminar and somebody is relying heavily on the structural form, they often have a robustness check where they try a lot of other functional forms.
Yeah.
Or do you?
Yeah, you can do that. But one of the things you want to make sure and let people know is, I'm testing this hypothesis. This hypothesis test is not predetermined by the functional form I've chosen.
As a small follow-up, is there any formal tests that would tell you, or is it entirely your imagination what the structure should be, or are there formal tests to say, oh, this is more likely than the other?
Well, there's formal tests that you can compare different structures and say, and a lot of structures are nested, so you can do likelihood ratio tests if you're doing maximum likelihood or something like that. That's a fairly simple test. But there's all sorts of statistics that you can use to compare different functional forms, and data scientists spend a lot of time on estimating complicated functions, and it's all they're all concerned about prediction. So they estimate a function with one sample, and then they use a separate sample to try to see how the functional form that then gives them the smallest error, root mean squared error when they apply it to data that they didn't actually estimate. But so that's one way you can do model selection. The other way is, there's EIC, AIC, likelihood ratio test if they're nested models. What's there? There's another one from non-nested models that I've used. May come back. But there are ways that you can compare the different models and say, okay, does this one? And another way that you'll find out that there's pretty big hint that it's not a very good structure, that you chose a structure that's not very good, is the model won't estimate it too, or you get really bad results. If you're using maximum likelihood, you may have convergence issues. If you're using OLS or something like that, you'll only get really, really small R squares. Okay, other questions? All right, so I'm running out of time, so I better hurry things up. Okay, so what do you need to estimate these models? Well, you need seeding rates, you need input prices, all input prices that are relevant. You need to know how many bushels of corn. For 7 and 8, you could do an instrumental variable analysis, assuming you don't have any, correlation between your errors and your prices. Equation 9, you need seeding rates, all input prices, price of corn. Again, presumably you can just use OLS because everything's supposed to be exogenous at that stage. We didn't really say, so this kind of, okay, structural, which of these models are structural, which of them are not structural? Again, right, 7 and 8, this is going to be a structural model, right? We haven't gotten rid of all the endogenous variables in equation 7, so it's a structural model in any context. This one, it's kind of a in between structural and reduced form, depending on which definition you prefer, right? We've solved for all the what we think are the exogenous variables, but there's plenty of economists who say, well, your assumption that these prices are not correlated with your error is foolishness, and you don't have a structural model. But these are actually endogenous variables that we need to do something more about. Okay. So, well, we've added structure. We saw how we could test these hypotheses using that added structure. What if we don't want to add structure? But we still want to be able to test our hypothesis. Okay, so let's not add structure. And let's keep things simple. So let's just define a linear function where we have this RF variable. This RF variable kind of depends on how we want to attack this problem, all right? But it's going to be some measure of fertilizer price, right? Then we're going to have a bunch of covariates here, right? And we have to select covariates so we get things like conditional, right, independence. If we don't have conditional independence when we select these covariates, then we're not going to satisfy the assumptions we need to in order to be identifying the parameter of interest, which is going to be this lambda f. All right. And then we're going to have this error term here. And this error term, depending on the method we use to try to estimate this equation, might be include fixed effects or other things. All right. Okay, so our hypothesis in this case is pretty straightforward. We just need to see, does the increase in the price of fertilizer, does that have a positive effect on our use of this input, which is, this input is the seeding rate, all right? So we just need to check if a delta or this lambda f is positive or negative, all right? So the big challenge now is to get an unbiased estimate of lambda f, all right? And that's all about, how do we do that? How do we do that in these contexts? How can we make sure we get an unbiased estimate of lambda f?
We have a RCT.
No, we could do an RCT. All right, so we could go and say, okay, well, let's randomly select farmers and give them a subsidy for their fertilizer that they use. Okay, and then so presumably those people who get a subsidy are paying a lower price for their fertilizer. And then we can compare those people with people who had to pay the normal price and say, okay, does that give us a positive or negative relationship? Do the people who got the subsidy, do they tend to use more, do a higher seeding rate or a lower seeding rate? Well, that would help us answer this question. So that's one way we could do that. That could be very expensive, particularly in a developing country like the U.S. But that's one way. Other ways that we could think about this?
I mean, to swing for the fences, if an RCT is one approach to do it, then wouldn't any observational study with the appropriate form, difference in difference, IV, as long as you have some kind of natural experiment or something to motivate that parameter?
Yeah, so quasi experimental methods. There's ways that we can, use panel data and use fixed effects to try and control for stuff. Right, that'd be another way, right? quasi experiment. So, did government put taxes on nitrogen fertilizer at some point in time that we could use a random discontinuity model based on, when this new policy came into effect? Are there states, or some states, do they tax fertilizer more than other states to where we could go along a border of a state, one that taxes and one that doesn't tax, and use, again, random discontinuity models to try to figure out, to use that to identify what this effect is. So there's lots of different ways, depending on what type of data is available, what types of policies are out there, that we might be able to estimate this equation here and figure out what this parameter is so we can test it. There's no structural assumptions here. This is pretty simple. I mean, it seems simple and straightforward, but of course, identification and coming up with instruments or coming up with a strategy that works, is a challenge. But this does stay away from the functional form. So, that was pretty much what I had to say. Right, we kind of hit all these, panel data using fixed effects, regression discontinuity, using fertilizer taxes, maybe, tax policy, randomized control trials, where we actually do an experiment in the field, or other quasi-experimental designs. A lot of this is going to depend on whether, what's better, structural versus, they both have their advantages. A lot of it's going to depend on what data is available and how much money you have to spend to collect data if it's not, the data you need is not available. Go ahead, Francis.
Yes, so I wonder, our department, we are basically trying to apply this, that, are there ways for us to, for example, in practice works to adapt, speak evolved structures so that we can, use their structures to do our estimations?
Can you? I mean, yeah. So, do you have a specific problem? I mean, I quite honestly, when I start thinking about empirical problems, I usually start with very general, just functional, general functional forms, and then I ask myself, okay, well, given these general functional forms and what I know, what information do I need? And I oftentimes do a survey. I end up doing surveys, and those surveys, what I've learned is trying to ask farmers all the prices and for all the inputs that they use to produce, and cost information or other information. That's very hard information to get. So I actually end up using a lot of reduced form estimation with survey data, because you're always going to have issues with omitted variable bias, because the more get all that information, it takes very long and arduous survey, and people don't, especially now, don't like to spend a lot of time on surveys. So unless you got a lot of money to pay them to do the survey, then you're not going to get the information you need to do a more structured.
One good thing about the structural model is you can do counterfactual analysis.
Yeah, no, that's right.
The trade-off is that you're imposing a lot of structure.
You're imposing a lot of structure. That structure is wrong. You're not, But again, that gets back to doing robustness analysis, where you look at a couple different structures and see if you get really big different answers.
That's something you can do with reduced form, because most of them are just like
that's right. Yeah, so the big issue with reduced form is external validity, right? The idea with a more structural equation is that you'll have more external validity, assuming your structural form is reasonably specified. That's right.
Sometimes you see folks who try and use simulations to try and get at some of this. So maybe they have a Monte Carlo simulation or like an agent-based model.
Yeah. In
your professional experience, do you find those kinds of arguments convincing, or do you think that they're trying to answer a different kind of question, and maybe that's a whole different set of lectures?
No, I've seen, some of my early work off of my dissertation is I actually used experiments to parameterize agents in an agent-based model, and then said, okay, how do these agents play the game? Because it's essentially a dynamic game of asymmetric information, and game theory says they should play it this way, but when I did the experiments, they didn't play it that way. And so I said, well, what's the issue? I said, is game, what's wrong? What's failing in game theory here? What part of game theory is failing here? So I had enough information that I could estimate best response functions empirically for this game, and then I could use those best response functions, essentially program agents, computer agents, to use those best response functions, and then just throw them in a pool and see, what happens, what equilibrium it play. And when I did that, the equilibrium concepts seem to be fine. The problem seemed to be that making the assumption of risk neutrality when you calculate your best response function in that game was not a good idea, because they were behaving as they're risk averse as opposed to risk neutral. Yeah, so that's, we can hush. We can scurry out of here since we're about ready to